the ICSI session on machine learning and models. My name is Liliana Pasquale and I will be the session chair for this ICSI session. The first talk is a journal first paper titled Improving Vulnerability Inspection Efficiency Using Active Learning, and the presenter is Tim Menzies from North Carolina State University.
Thank you for that introduction. Welcome to the virtual world of ICSI. Let's see now, it's not working. Present. There we go. So I want to talk about active learning and finding bugs fast, particularly security bugs. This is work with myself, Laurie Williams. Goguryeo was the lead on this. He's now at Rochester State Institute of Technology, and Chris Tyson, who's now at Microsoft. What we're about is security problems, and it really is, I don't think I need to motivate the idea that we need better ways to do security in software engineering. When you look at the number of people affected by security breaches, literally hospital rooms brought down, people not being treated, I don't think I need to motivate the need for more security in the current world. The problem is, if you look at what the number of actual security related bugs, they're very rare in the whole space. What you're looking at here is Mozilla, and the pink are where you actually find security bugs. And the thing we want to say here is that this is like needles in a haystack. The security bugs we're after are very small in number. Now, if you look at current results on what people have done, you see situations where we either get very high recall, which is to say we find all the bugs, but very bad precision. Very bad precision would mean the more bugs I give you, you waste your time looking at things that aren't actually bugs. Or you get very high precision, which is to say that everything I show you is likely to be a security bug. However, we miss most of the bugs. So these are things we want to avoid. So we have this problem where there's really cheap, low cost, low accuracy ways to do this stuff. But if you go to human beings and experts who actually know this stuff, these people can find these security flaws for us. However, they have a problem. They're expensive. Human expertise is very expensive. And so you've got this twin capabilities. You've got machine learners that can do things at low cost, but low accuracy. You've got human beings that can do things at high cost and at high accuracy. So why not put the two of them together? And this is this idea of active learning, where if you take examples, you put them into an AI, gives some reports, humans reflect on the reports and say, I think you're talking nonsense. And based on feedback from the human, things go back and cycle around this loop again and again and again. And so if you look at an active learning framework, you've got initial sampling. This divides up into three problems. If you and an AI sit down to solve a problem together, you want to look at fewer examples and find more of the problems. And so this is the detect more and inspect less phase. Another thing we want to say is that if humans and an AI get together to solve a problem together, there's a stopping problem. You need some rule for saying, we've done enough, let's not look at any more. Further, if your humans and AI get together, AIs make mistakes, but so do people. If you look at the statistics on the number of poor labels produced by people, it's really clear that when humans look at something and say, that's an Australian, that's an American, that's a security bug, that isn't a security bug, they make mistakes. So if you're going to do human and AI interaction, you want to be able to reduce the effort of the humans. That's the detect, inspect less and detect more. You need a stopping rule, and you need to handle human errors. And all those come together in the tool that we built. It's an incremental active learning thing. Internally, it's a support vector machine. As examples show up, the support vector is rerun, and the model gets updated all the time. We reflect over the model to decide what example to grab next. If you're worried about continuously updating a support vector machine each time a new example shows up, do not be worried about that. The complexity of running support vector machines is actually the complexity of the support vectors. And what we're finding for all these data sets is you do this large analysis, you're typically running with, often less than 100 support vectors, often less than 12 support vectors. Now, when we compare our approach to other people, like humans reading everything, the top line of this is if humans read everything, that's the most expensive, that's 100% cost, humans reading everything. And let's say the humans are perfect at finding security bugs. There are various methods in the literature discussing how to improve on that. And so that's the Shin and Walden work. However, that work has a certain hidden trap. That work produces precision and recall numbers and cost numbers, but the cost ignores the cost of a human labeling the example. So there's this secret when you do supervised learning. Someone has to go through and label the examples. And typically what we do in research is we reuse other people's labels. And when those labels are wrong, our subsequent research is wrong. We think that labeling is a first-class problem, is a first-class issue. And so what we do now is that we ask, we put the labeling into the process. Humans and AI are getting together doing the labels. Now, when we get humans and our method together, the last two lines of this chart, we see that where humans read about 13 to 20% of the code, and we find about 85 to 90% of the bugs with this method. And so if you want a quick summary of what we're talking about here, machines are great, humans are great, but putting them together, you can achieve much more than doing them separately. And that's my talk. Any questions?
Thank you very much. We have a question from the audience. So could you briefly explain how the AI plus humans are solving the problem together in your work?
Yes, let's you and I go into the world and look for a really good restaurant. And we'll walk around at random and we'll go to restaurant 1. And you'll say, this is a terrible restaurant. And I will use that feedback to pick the next restaurant. And if I go to the next restaurant, you look at it and say, I hate that restaurant as well. So then I use your feedback to guide our search. After a while, hopefully I lead you away from very bad restaurants. Internally, this is an incremental support vector machine. Examples come in one by one and the human classifies them. So what we get is a sigmoid curve of performance where initially there's no improvement, and then we turn the corner and we begin to classify what's a good security problem or not. And then after a while, we turn another corner, we're no longer improving anymore.
So we have another question from the audience. So what about precision results?
Well, you optimize for what you want. If really, I almost have a statement about we want to stop using precision for sparse problems. Consider if you look through 3 Google pages to find what you want, you've just glanced through 30 things and you found one thing that you want. So that session with Google where you look through 3 pages has a precision of 3 on 1 on 30. It looks very low. But because it's so quick to do, you don't care that it's low precision results.
Okay. And we have time for a last quick question. Is this applicable to deep learning-based techniques?
Anything where humans and AI get together and you have to do the incremental labeling, this is the way to speed it up. This is a general framework for human-computer interaction and analytics.
Okay, so let's thank again the speaker. Thank you, Tim. And let's move to the next paper. The next paper is a journal first paper, which is titled How Bugs Are Born, a model to identify how bugs are introduced in software components. And the speaker is Gemma Rodriguez.
Thank you. Thank you, Lilian, for the introduction. Hi, everyone. I'm Gemma Rodriguez from the University of Waterloo, and I'm going to present a recent empirical software engineering paper, How Bugs Are Born. This is a collaborative work with the great professors Goguryeo Robles, Jesus Maria González Barahona, Andy Seidman, Alexander Serebrennik, and Daniel Herman. Due to time constraints, I only can present a brief overview of the paper, but I encourage you to read it and ask me any question you might have. I will be very glad to answer them. So let's start. In this paper, we study how bugs are introduced based on information available in the development repositories. Here, it's very important to mention that we only focused on bugs that have been recognized as bugs by knowledgeable people from the project. So we have removed feature requests and bugs in test files from our analysis. In the paper, we have proposed a theoretical model with a specific criteria for deciding if some change introduced a bug. The criteria is, did the change cause a bug when it was included in the code base? Finally, we operationalized our proposed model and empirical evaluated it in 2 open source projects to find the origin of 116 bugs. With the criteria that I just mentioned, we tried to decide if a change really introduced a bug when it was written and submitted the first time, or if the change was right at the time of being written and it was later changed to fix a bug. This criteria is very important because it leads to the concept of extrinsic and intrinsic bugs. While an intrinsic bug is originated within the software, an extrinsic bug is originated because of changes in the environment where the software is created or run. So let's see an example. Here we can see 2 very different versions of the project. The project is PA, and this project uses an external library. In this case, it's NumPy library. So just think about the different versions of the project presented in the below slide as the outcome of the Git log. So each version is the state of the project after making a change. In this example, we can see that there is a bug that has been fixed. So to identify the origin of the bug, we first analyze the lines that have been modified to fix a bug. These lines pointed out to a potential bug introducing change, the BIC of the slide. We then apply our criteria to that change, and in this case, we identify that the bug is intrinsic, as the potential bug introducing change, the BIC, was using the NumPy library incorrectly, which caused the bug. However, in this other example, after applying the criteria to the FFC in this case, because it's not a bug introducing change, we see that the change was using the NumPy library correctly at the time of being written. So the library, after that change, the library changed its API, and this causes that our project exhibits the bug. So in this case, this bug is external because the bug was caused by an external API change, not by a change in our project. So our theoretical model asserts some assumptions, which are needed for the definitions and methodology proposed. But these assumptions are very close to what practical real system shows. For example, we assume that the project have a control version system. A key concept we introduce is the perfect test for a bug. Intuitively, it's like a regression test designed to test for a bug. But it's perfect in the sense that if applied to a change on the source code, it will fail if and only if the bug is present. So to evaluate our proposed model, we operationalize it and apply it to 2 open source projects to identify the origin of 116 bugs. We use information available in the version control system, the issue tracking system, and the code review system. First, we identify the bug fixing commit, and then with all the information available, we mentally build the perfect test. We analyze the previous versions of the software with the perfect test in mind to identify if the version will pass the test or not. So then, depending on the context, we identify whether that version introduced a bug in the software at the time of being written or not. This operationalization of our model helps us to create a manually curated dataset that we then use to evaluate how well 4 current algorithms perform when identifying the origin of bugs. Our results indicated that the criteria defined in the model enable us to classify bugs as intrinsic or extrinsic. Also, for the 116 bugs, we found that 9 to 21% of them were extrinsic, meaning that they don't have a bug introducing change in the version control system. Finally, we found that the best algorithm actually correct for 61 to 63 of the changes identified as the origin of the bug. So finally, as a takeaway, I would like to mention that first, there are intrinsic and extrinsic bugs. So we cannot assume that the lines changed to fix a bug are the ones which introduce the buggy code. And this is very important because these results have many implications in software engineering. Many previous studies, software tools, and review practices assume that all bugs are of an intrinsic nature. Thank you for listening, and I'm glad to answer your questions.
Thank you very much. Thank you very much. So we have some time for question. And the first question is that is related to when manually analyzing bug, how many times the bug had an unclear source, and how have you managed this situation?
Sorry, can you repeat how many times?
So how many and how you manage a situation in which a bug had an unclear source?
Yeah, so we carefully analyze all the textual information. We have another category which says that we don't really know because we will need more analysis or automatic tools to be able to be sure that these are an extrinsic or extrinsic bug. So in our paper, we have three categories. Like we are sure this is intrinsic, we are sure this is extrinsic, and we cannot with the current information.
Okay. So we have also a similar question. So may it happen that an extrinsic bugs are also intrinsic? So when updated the internal bit script regarding the use version of the library?
Yeah, so mainly what extrinsic bugs means for us is that if the change that is pointed out as the cause of the bug was written correctly at the time of being committed, this is extrinsic bug. So if that commit introduced the bug when it was written, it's intrinsic.
Okay, we have time for a very last question. So how long it took to analyze the repository, and how many repositories did you analyze?
Yeah, we analyzed two projects, Nova and OpenStack, and it took us a long period of time. So this work started around 2 years before it was published. So we have to be sure that the bugs we analyze, we really know that they are intrinsic or extrinsic. So the process was repeatedly several times until we can be sure that our data is correct.
Okay, thank you very much. There are more questions on the chat, and maybe you can go and check them later.
Yeah, sure.
Thank you. So let's give space to the next speaker. This is again a journal first presentation. And the title of the presentation is How to Dodge Complex Software Analytics. And the presenter is again, for the second time, Tim Menzies from North Carolina State University.
Hi, so again, hello again. So I'm not doing slides. Everyone can see my background? Fantastic. So what I want to talk about is hyperparameter optimization. This is work with Amrit Agarwal, Wei Fu, Scott Chen, Chaipeng Chen, and myself from NC State University. My problem is over here. Here we see a bunch of machine learning algorithms that have been customized. We say that you shouldn't use things off the shelf without customizing them. Here is an interesting piece of paper we all know about these days, the mask. This was, when it started out its life, a generic piece of paper. So before you use a generic piece of paper for a particular source task, you want to customize it. Customizing machine learning means adjusting the control parameters, the hyperparameter optimization parameters. So over here, you see the effects of that. Can you see a little blue circle called C5.0? That's its performance before tuning. And can you see up there a little red triangle? Its performance after tuning is doing dramatically better. So tuning is a really good thing. It should always be done. The problem is the number of tuning options. If you look up there at 2, I can't even show you on the screen how many pre-processing options there are, how many learners there are. There's just too many options to show. There's literally billions of options shown up there in number 2. So how do I explore those in real time? And this is an interesting problem because as our learners get slower, say with deep learning, as we want to do 20 repeats for statistical validity, as we're running over multiple data sets, we really want to explore billions of hyperparameter options in reasonable times. Our trick is based on what I'm showing you up there in 3. Up there in 3, I've run a learner twice on 90% of the data shown at random. Can you see the blue and the green curves? They're up there top right. And what you see is the same learner has slightly different performance. The blue and the green curve comes from the same learner. There's a wriggle when you run learners multiple times. And after a certain point, after some epsilon, you can't distinguish between the performance of learner 1 and learner 2 because of its epsilon. Now, this is not a bug. This can be levered. Over here in 4, you see I've divided the recall and false alarm space into squares of epsilon of size 0.2. So here I'm assuming that I can't distinguish between the performance of 2 learners if their performance difference is less than 0.2 measured in terms of recall or false alarm. Now, here's the important thing. What I notice in 4 is I have 25 possible outputs. The recall false alarm space has been divided up into 0.2. What I notice over here is I have billions of input options to my hyperparameter optimization. Therefore, I ask you rhetorically, what do you want to explore? 25 options here of equivalent outputs or billions of possible inputs. So what we actually do is we explore this space. And what we do is we do a taboo search. We pick from this space at random and do something. Just write down the results. Then we pick from this space again and do something else. And if the second thing falls within, say, 0.2 of the first thing, we mark those 2 options as boring. We then keep picking from this space, stepping away from the boring options. And after a very small number of evaluations, 30, 40, we find we can explore this space very effectively. We've tried this for these applications: defect prediction, effort estimation, GitHub issue close time, bad smell detection, text mining of issue reports. And I can tell you that this taboo search across a small number of equivalent outputs does as well as some sort of GA or NSGA2 or MOEAD search of this large number of options. Above me, you can see the runtimes, the blue curves. The bottom blue curve here shows the results of using a GA on this thing, and it's the largest curve. And up here, you can see the tiny number of evaluations needed to achieve. So you can dodge complex software analytics. You don't have to explore billions and billions of options because many of them have equivalent outputs. Many roads lead to Rome. So what we're recommending when people do, if you want to have the benefits of hyperparameter optimization and you don't want to get lost in exploring billions of options, do a taboo search across the output space. And wow, I'm finished a minute early. So what I'll say is we've been looking in other papers on when this all fails. What are properties of data sets for which this kind of taboo search is not successful, and you really do have to explore hundreds of thousands of options in this space. And we're looking ahead at something called intrinsic dimensionality. Think PCA, the space, but a bit more sophisticated than that. And we think it's possible to predict for the kind of data sets that's amenable to this kind of quick dodge analysis. And it turns out a lot of software engineering data sets, for reasons that Prem Devenbu is telling us about with naturalness, are naturally amenable to this kind of very fast speed up. Just to finish, up here is a URL, tiny.cc-dodge20. All the links in this talk are available there at tiny.cc-dodge20. So let me take your questions now.
Yeah, so thank you, Tim. So we have a question. Is there a plugin or R package or something similar where the approach is automated and usable?
All our code is available online. If you go to this TSE paper, you will find we have GitHub packages. But honestly, you could code this up yourself. Just do a recursive k=2 means across the output space, and you'll get all the similar things put together. And then just pick at random from the leaves of that space and avoid things you've picked at before.
Okay, so we have time for a last question. You believe the intrinsic dimension of the space is much smaller than what it should be. Is this a surprising observation?
No. If you look at the nature of software engineering, we got lucky when we chose language in the 50s to represent programs. Language is a technology evolved for millions of years where we have intrinsic dimensionality. It has a simpler underlying form, and that's how we communicate, and that's how we have error correction because of its simpler underlying nature. Many software engineering data sets are inherently simple, and we've made things far more complicated than they need to be for many tasks.
So maybe a very last question. So What does the result say about the underlying complexity of software analytics?
It means you should be reading more of my papers. We've been saying for the last 10 years that there's an underlying simplicity, that a lot of what we're doing is like dancing on the foam of an ocean. And underneath, there's a simpler structure. And people are obsessed with complexity and making things more complicated. For complex visual things like cars, we need deep learning, absolutely. But for many other tasks, less is more.
Okay, so we can close with this sentence, less is more, and move to the next presentation. This is a technical paper, which is titled Important-Driven Deep Learning System Testing. And the presenter is Simos Gerasimou from University of York.
Hello, everyone. Can you see my screen?
Not yet.
I can.
Yes, now yes. All
right. So hello, everyone. I'm Simos Gerasimou from the University of York, and this is a joint work with Hassan and Iser from Max Planck in Germany, Albert Sen and Albert Hagan from Boğaziçi University in Turkey. So this is a quite simple technique for testing the adequacy of deep learning systems and the corresponding training and test set. So just to motivate a bit the work, we all live the work of ubiquitous and intelligent computing, where there are, we want there is a bright future and huge potential for autonomous systems. And these systems, they can modify their behavior and internal structure in response to changing environmental conditions, evolving requirements, and internal changes. So these type of systems, they are typically deployed to perform tedious, repetitive, or dangerous tasks and achieve improvements in safety, reduce cost, energy resources, and in general benefit society. Some typical examples include, as you well know, driverless cars, robot harvesting machines, intelligent chatbots, aerial and water vehicles used for inspection and maintenance. Now, one way or another, all these systems, they use a reference closed-loop model under the hood through which they can steer adaptation. They enable their autonomy by by sensing the environment and the relevant context, making inference, reasoning, classification, and so on and so forth, making decisions and planning, and finally acting by adopting a selected strategy or informing the relevant and interested stakeholders. Now, as it has been evident in the last decade, there has been a need or leveraging the powerful capabilities of deep learning systems and delegating to some extent the understanding and decision making to these machine learning artifacts is it seems a prominent way to go forward and realize the potential of autonomous systems. At the same time, though, there are many challenges that need to be resolved. For instance, the difference between the real world and model-based view, the need for interpretability, robustness, verification, and validation. In this work, we started from let's say the standards where they define testing and verification testing as a primary artifact for assessing the capabilities of these type of systems, and we leverage recent research from the interpretability domain in order to test the adequacy and the robustness and guide the verification and validation of deep learning systems. So someone in a recent race workshop, Xinyu said that it would be nice we should learn more from what machine learning researchers are doing in order to leverage their developments and their advances. So What is deep importance in a nutshell? It's a systematic testing methodology accompanied by an importance-driven test adequacy criterion for deep learning systems based on relevance propagation. And this I will explain in a bit what we mean by that. And this is what comes from the interpretability domain of machine learning. Essentially, by analyzing the activity of a deep learning system and its internal neuron behaviors, deep importance develops a layer-wise functional understanding of the internal neuron behavior that signifies the contribution of those internal neurons to the output through the layers. And these contributions enables to determine the causal relationship to some extent between the neurons and the deep learning system behavior. Since more influential neurons, they have a stronger causal relationship and can explain which high-level features influence more the decision-making. And in deep importance establishes this relationship by computing a decomposition of the decision made by the deep learning system, and iteratively from the output layer to the input layer, redistributing the relevance in a layer-wise manner proportional to how prominent each neuron and its connections are. So in the next step, using those important neurons, once those important neurons have been identified, deep importance carries out a neuron-wise quantization or clustering, if you prefer, in the software engineering domain, to partition the space of those neurons into automatically determined finite set of clusters that capture this behavior to a sufficient level of granularity. And the importance, in the final step, the importance-driven adequacy criteria, which is instrumented by deep importance, measure the adequacy of an input set as a ratio of combinations of important neurons clusters that are covered by that set. So what do we mean by the deep importance and by underpinning principle of deep importance? It's we want to show that it's quite different from the neuron activation values than the neuron contribution to decision making. So if you the neuron activation values, which are shown here on the left hand of the left hand side of the box plot, you can see that they are quite different from the neuron relevance scores that are signify which parts, how prominent each neuron contributes to the decision making. So in a sentence, deep importance targets the identification of the most influential neurons, and those are the neurons that should be tested more thoroughly. So as I explained earlier, then we have in the first step, we find the neurons that are key contributors to decision making. We leverage layer-wise relevant propagation to find the neurons' importance. But in general, we can leverage other explainability techniques like deep lift, left to explain, LIME, and so on and so forth. This is a general framework that can be employ other explainability techniques. And the intuition under the hood is that neurons with higher activation values, they receive a larger relevance contribution, and the more relevance flows through more important neurons. Once this step finishes, we return the top important neurons, which are the key contributors to decision making. In the next step, having identified those important neurons, we realize an iterative and supervised learning technique. In this paper, we used nearest neighbors instrumented with a silhouette score, but other techniques for clustering and internal validity or external validity scores and measures can be used in order to cluster the vector of activation values for the most important neurons into a finite set of clusters. And the primary purpose of that is to optimize the inter-cluster cohesion, meaning the average distance, minimize the average distance of the activation value to all other values of a neuron's activation value, given that input to all other values in the same cluster, and the inter-cluster separation, In this case, is the average distance between the input activation value and activation values in their nearest neighbor clusters. And what we end up by applying this is we have clusters for those important neurons based on their activation values. And it's important to highlight that cluster numbers can be different between important neurons. And the final step, we apply the importance-driven coverage, which we have the combinatorial, what we call the important neuron cluster combinations. Essentially, it's a combinatorial, it's a Cartesian product of the clusters of the important neurons that have been identified before. And we have also the importance-driven coverage metric, which essentially measures the ratio of important neuron cluster combinations that covered by the testing set over the size of the important neural cluster combinations. And as and there is a proof available on the website which shows that the IDC metric is sound, meaning that for any new input that exercises a new neuron cluster combination, the IDC metric will increase. Of course, thank you. So we evaluated deep importance on 3 different data sets: NIST, Cypher-10, Udacity, self-driving car. And we use different number of important neurons, which is the only hyperparameter of deep importance, and compare it against state-of-the-art coverage criteria, meaning deep explore, deep gauge, surprise adequacy. And we also synthesize new inputs given the training, using as input the training set using Gaussian-like white noise, and adversarial inputs using state-of-the-art adversarial generation techniques. I don't have too much time to go into the whole evaluation, but feel free to read the paper and go to the website, which has more information. But it's important to highlight that in this we have a set of research questions, but it's important to highlight in the first research question, where we evaluated whether deep importance can really identify those neurons that are key contributors to the decision making. And in this case, we found deep importance neurons are found by deep importance and compared it against neurons selected randomly. Then we modified the inputs, input 2% of an input image, and then compare the distance on the activation values from those neurons. And as you can see, there is a clear difference between those activation values, showing that deep importance can detect the most important neurons of a deep learning system, and those neurons are more sensitive to changes in the relevant pixels of an input. And closing, we also evaluated whether deep importance can inform the selection of a diverse test set. To do that, we modified the original test set with.
Your time is over.
All right, sorry for that. So I highly, just to conclude, there is a website, please go and read it. There is a lot of work going on in order to improve deep importance. And if you have any questions, just please let us know. Thank you.
Thank you, Simos. So let's move to the next paper. This is a technical paper, which is titled Quickly Generating Diverse Valid Test Inputs with Reinforcement Learning. And the presenter is Caroline Lemieux from University of Berkeley.
Thank you. Can you hear me?
Yes.
Okay, and let me share my screen. Can you see my slides? All right, yep. Everything good?
Yep.
Okay, so thank you very much for the introduction. Today I'll be talking to you about RL check. So you may know that programs have bugs, and bugs can be very bad if they're in the wrong software component because they can lead to very expensive consequences or even cause security vulnerabilities. And the annoying thing about bugs is they have all these consequences, and they can be hard to find by just humans staring at code ahead of time. One of the best ways, or one of the very powerful ways we have to actually find bugs in programs, is to find inputs, which when the program is run on that input, cause the program to crash or have an assertion failure or otherwise reveal a bug. And what we've seen in recent years is the emergence of a bunch of fuzz testing tools, which have been adopted quite widely across industry and open source in order to generate inputs which reveal bugs or other important program behaviors very quickly. So today, I'm going to talk to you about a particular type of fuzz testing or fuzzing called generator-based fuzzing. And I'm going to talk about the fundamental trade-off in the efficiency of that kind of generator-based fuzzing and how RLCheck is really trying to address that problem. So let me get started. You may have heard the term fuzzing which harkens back to the 90s when Barton Miller and others figured out that if you just sent a bunch of sequences of random garbage characters to popular Unix utilities, just pure random characters, eventually some sequence of random characters caused those popular Unix utilities to crash. And that's what birthed the term fuzzing, this technique of sending random characters to programs. Now, in the 30 years since 1990, this is no longer very effective at fuzzing, at finding bugs in complex programs like, say, the Google closure compiler, which expects JavaScript as inputs. Because regardless of your opinions of JavaScript, if you just send this compiler pure random garbage characters that are look nothing like JavaScript, the compiler can see that, and it'll just return early, and you won't have any very interesting inputs being generated and no interesting bugs being found. So the idea of generator-based fuzzing is to replace this random source that's just producing random sequences of characters for inputs with an input generator, which is a non-deterministic function that each time you call it, returns a kind of random-looking input within some search space of interest. In this case, maybe JavaScript programs, such that your program under test actually does something a little interesting. Now, to get into all the details of generator-based fuzzing, we're going to look at a much, much simpler example. And let's consider a case where the inputs to our program are binary trees. The reason for this is because I can show you a binary tree generator on a single slide. It may look a little like this. To randomly get a binary tree, we will randomly choose a value to put in the root of the binary tree. Then we'll randomly choose whether to generate a left child. If we do, we might recursively call this function to generate the left child, and so on and so forth for the right child. Now, let's look at the kind of program that might take in these binary trees. In particular, let's assume that the thing we're trying to test is the binary search tree insertion property. And basically, we're going to use this handy little assume statement, which returns early without failing if its input expression is false. So in this case, this assume statement returns early if the tree generated given to the test driver is not a binary search tree. Now, the nice thing about this is we can use just our regular binary tree generator, which was very, very simple, to generate hundreds or thousands of binary trees, and the ones that aren't binary search trees will just get rejected at this assume statement, and we'll be on our merry way to test this driver with many binary search trees, right? Well, that kind of depends on how many rejections we're going to end up having. And this brings me to kind of the fundamental trade-off we have in generator-based fuzzing. What is the probability of generating a binary search tree if we're at this kind of generation state? Well, a binary search tree has to have its left children have smaller values than their parents, amongst other things, which means that for the value of this green node, the only values that could possibly lead to a valid binary search tree are 0 and 1, which means we already have a chance of less than 9% of generating a valid input for just this very small input. So you can see that with just naive binary tree generator, we're not going to generate very many valid binary search trees. It's going to take forever to generate any of them that are like mildly large or interesting. And we could spend a bunch of time tuning this generator to make sure that it only generates binary search trees. But that's effort we won't be able to use to programs that take other types of binary trees. And if we're actually looking at a real software component that has a much more complex assumption on its test driver, that might be prohibitively expensive for a human. So this trade-off is what RLCheck is trying to address by basically automatically tuning generators so that we can quickly generate many different valid inputs without having to change the code. The high-level idea is that instead of generators just returning random inputs on their own in their search space, we have some sort of guidance which is looking at what the generator has done in the past and using that information to guide the generator towards producing more valid and unique inputs. Now, the insight here is that if we want our generators to say return a valid input in this case, really we just want to make the generator, choose 0 and 1 in this case without having to modify the code so that we actually have to have min and maxes on these bounds or whatever other way you could think of modifying this generator to impose this condition. The insight is that the input we get from the generator is fundamentally driven by the choices the generator takes. So what we want to do is just simply guide these choices so that instead of being random, we are choosing values that maximize the chance of generating a valid input. Now you can imagine there's not always one good value to choose, right? The good value for each choice point depends on the context of that choice. What I mean by that, right, if you're the left child of a 2, good choices for the value are 0 and 1. If you're the right child, it's everything greater than 2, and so on and so forth in different contexts. So actually the problem that we're going to solve in RLCheck is to make best choices given some context. So basically we replace those random decisions with a guided decision that is conditioned on the current context. I don't have time to go into exactly what this context is. But the tool we use to solve this is we use an RL agent at each choice point that learns over time to take choices that produce more valid and unique inputs given a certain context. We actually just use plain table-based Q-learning, not deep learning here. And the nice thing about it is that our agents are rewarded with just information about inputs being valid and syntactically unique. So we don't need to instrument programs. And that means that we can really run generator-based fuzzing at full speed and quickly generate orders of magnitude more unique valid inputs than prior work. So on the y-axis here, we have the number of basically path unique valid inputs. And you can see that RLCheck in the green is generating orders of magnitude more unique valid inputs for the Google closure benchmark compared to plain generator-based fuzzing in the blue and our prior work Zest, which was a evolutionary approach guided by coverage. And we saw similar results on other benchmarks, including Ant and Maven on the top, which are basically restrictions on XML documents. So these are not just, this doesn't just work for binary search trees. Just to wrap up, the point is that generator-based fuzzing is really, really effective at finding bugs, but it requires a well-tuned generator to work well. And we've seen some promise in RLCheck of using an RL inspired approach to kind of tune generators more effectively. You can find the paper and the artifacts at these links, and I'm happy to take any questions.
Thank you very much. So we have a few questions lined up. So the first question is about generator-based fuzzing is what people have called automated test input generation for a while. Can you explain the differences between the two?
I think so my understanding of automated test input generation is indeed that you are generator-based fuzzing is a subset of there are many different ways to create test inputs automatically. Generator-based fuzzing is just the practice of, it's also called property-based testing, but I'm using the term generator-based fuzzing a bit more broadly here to mean any case where the way you're generating test inputs is by having kind of a non-deterministic function that you're sampling from to create different test inputs. You can kind of consider that like grammar-based input generation is pretty similar to what I'm calling generator-based fuzzing.
We have another question. So are there multiple agents for each decision, or a single agent making many decisions at once?
So what we have in this prototype is just a single agent for each choice point that is learning basically to take actions, because all the different choice points may have, in this case, on the upper right, we have a choice point where you have to choose an integer value, in other cases where you have to choose Boolean values. So we have different agents at each of those points learning from their action spaces. Since we're not using deep learning, this wasn't really too expensive to train.
Okay, we have another comment, Grid Talk. Have you tried using more elegant reward functions like the code coverage, for example?
Yeah, so interesting thing about code coverage, you can actually find a study about this in the paper. If you teach it to like reward just increasing, say the branches covered, it will find that if it generates very, very, very large inputs, that quickly increases code coverage. And then you actually have a huge slowdown in the speed of input generation. So there might be something a bit better between just looking at validity and uniqueness, but this table-based RL was not really smart enough to learn anything other than just generate a huge input to try to increase branch coverage. Okay,
we have time for a quick question. Why tabular instead of DQN-based reinforcement learning approach?
So tabular was like one of the first things we tried, and it worked pretty well. Since then, I've actually explored with an other undergrad trying to use a DQN approach. The big challenge there is just like it takes a lot longer to start up DQN. And if we compare it to the tools that it takes a lot longer to train. So if you compare it to the power of, say, a regular evolutionary algorithm, the advantages you get, like, it was kind of too slow in our case.
Okay, thank you very much. So we can give space for the last paper. This is a journal first paper titled Impact of Discretization Noise of the Dependent Variable on Machine Learning Classifiers in Software Engineering. And the speaker is Gopi Krishnas Rajabadur.
I'll start sharing my screen now. Can you see my screen? Okay. Greetings, everyone. My name is Gopi Krishnan Rajbahadur. Today, I'll be presenting our TSE paper, Impact of Discretization Noise of the Dependent Variable on Machine Learning Classifiers in Software Engineering. So I'm finally a PhD student working with Professor Ahmed Hassan in Queen's University. And this work was collaboratively done with Professor Xiaowei Wang and Professor Yasuda Kame. Now, getting into the core of the paper. So discretizing the dependent variable is an extremely common practice in software engineering. Consider this problem of practitioners wanting to predict the popularity of an app in Google Play Store. So the first thing anyone does is take all the apps, sort the app ratings, cut it at a random cut point, and call everything less than the cut point as low rated and everything more than the cut point as high rated. In this example, I show the cut point being at 4 stars. But what about these two apps? One app has 3.9 stars and one app has 4.1 stars. In reality, it's not much different. If you were downloading an app, you wouldn't really even notice the difference. But for our training purposes, the app with 3.9 stars would be considered as a low-rated app, whereas the app with 4.1 stars would be considered as a high-rated app. So these have confusing loyalties, right? So we argue that there are a bunch of points that has confusing class loyalties around the cut point within some arbitrary limit. And we call these points as noisy points, and this area is noisy area, and the noise generated by these noisy points as the discretization noise. So an immediate question that follows is, what did prior research do about it, right? So prior research either discards the noisy points around the cut point, or they include all of it. However, both of these approaches have limitations. In one case, we incur data loss. There might be some useful points that we're throwing away. And in another case, we're including noisy data into the analysis. So what we do is we propose a fully customizable framework that helps you determine how much noisy data that you need to discard around your threshold for your classifier and your data set. And we make this openly available so that people can easily use it. So here I present the overall view of our framework. Though in the next few slides, I will take us through the case studies that we did with the data sets and the classifiers that we chose. You can use our framework for any data set that you bring in and for any classifier and determine how much data points around the cut point you need to throw away. So for data sets, we use 7 different software engineering data sets with data points ranging up to 70,000 and the number of features ranging up to 28. And for classifiers, we chose 4 commonly used classifiers in software analytics. And for performance measures, we measured the impact in terms of both threshold-dependent measures like precision recall and threshold-independent measures, so to get a balanced overview. And for cut points, because we lack the deep domain expertise for many of these data sets, we chose 3 data-driven cut points, and we studied the impact of the discretization noise generated by these different cut points. And finally, as I told earlier, we need to determine a limit or the amount in which the noisy area exists around the cut point. So we use an automated limit estimation algorithm to determine the amount of noisy area around the chosen cut points. There's more details about this in the paper. And we call this area as the noisy area. And finally, moving on to how our framework works, first, we take the whole data set, we cut it at the cut point and build a classifier. And we call this the classifier all. And then we start discarding noise from the noisy area in increments of step size. This step size determines the granularity of the analysis. And each time when after discarding the amount determined by step size, we compute the performance of a classifier that is built on the data without this data points. And we call this classifier step size. And we keep doing this in increments, and at each step, we compare the performance of the classifier step size with the classifier all that was built on the whole data set. And if at any step, the performance of this classifier step size starts becoming better than the classifier trained on all the data, we discard the noise that is given by the step size. And even after going through all of the noisy area, we are not able to, we don't find that classifier step size outperforms classifier all, then no data point is discarded. So with this, what do we find? We find that inclusion and exclusion of noisy area can both positively and negatively impact the performance. What it means is, depending on your case, you might be okay with using the whole data set, or you might have to discard a certain amount of data point around your threshold. For instance, when noisy points were discarded, we were able to notice performance impacts of up to 139% in terms of recall. And in terms of other performance measures, we were able to see impacts up to 60%. So if there's one thing that I can tell as a summary of our paper, please use our framework to see how much noisy point you have to discard around your cut point. And finally, if you think this whole idea of discretizing is the problem, we have another paper in MSR where we talk how we can use regression-based classifiers to avoid this whole problem of discretizing the dependent variable so there's no noise that is generated. So you can check it out. So to summarize, I first spoke about what is discretization noise and how it's commonly introduced in software engineering datasets and software analytics. And then I took us through our framework that we use to determine how much data points to discard around the cut point, and it's customizable. And we also saw that we could see impacts up to 139% in terms of recall when noisy points are discarded. So finally, use our framework before doing any analysis. I'm Gopi. I'll be happy to take any questions that you have.
Thank you, Gopi. We have a question from the audience. Nice talk. What sort of input does the framework need?
It needs the data set that you're using, the classifier. If you have the limits, you can determine your limits, or the framework can automatically estimate the limits to estimate the noisy points. And then you need the cut point that you're using. And that's all. Okay,
so the last question is, how the domain distribution affects the performance of the classifier? The domain distribution.
So it depends, it greatly affects the performance of the classifier, and that is why you need to run the framework for your particular case, because the results differ across each domain, each dataset, each classifier, and each cut point you choose. It's always good to run the framework in your context, in your domain, before making a decision. And that's why we don't make a generalized statement of how it affects different domains. Rather, we provide this framework as a tool.
Okay, thank you very much. Let's thank all the speakers and thank you for attending this session.
I would wait for the countdown.
Oh.
Hello, everyone. My name is Puyan Jamshidi, and I'm the session chair of the most exciting session at ICSI, Performance and Analysis. We have 7 presentations here, including I'm featuring 1 demo, 1 technical paper, 4 journal fairs, and 1 year paper. The first one is a demo. It's called Nimbus, Improving the Developer Experience for Serverless Applications. And we show the demo right now. Thanks.
Nimbus is a tool that aims to improve the developer experience for programmers developing applications that are deployed as serverless functions. Serverless functions, popularized by AWS Lambda, allow applications to be broken up into individual functions that can be invoked and scaled individually. As this is still a relatively new technology, there are some pain points when developing applications. For example, you generally end up writing a lot of boilerplate code, like handling serialization. Also, you end up having to use the cloud provider's SDK to interact with the deployed resources, for example, when storing items in a data store like DynamoDB or S3, which means that it becomes very difficult to migrate to a different cloud provider. Once your code is written, you then have to deploy the application. This generally requires writing a large configuration file, which is usually cloud provider specific. Debugging errors in this file is difficult, as there is no immediate verification, and deployment can take minutes before reporting the error back to you. Another common complaint when developing serverless applications is that there is a lack of tooling when it comes to testing, and specifically integration testing. Nimbus is a tool that we developed to solve these problems for Java serverless applications. Using Nimbus, the code and deployment configuration is much more concise. Many configuration errors are prevented at compile time without having to wait for long deployments. Nimbus provides functionality to test the integration of functions and other resources, and to deploy the application locally. Nimbus also does some optimization to speed up how long an individual deployment takes. Here is an example function written with Nimbus. This Java function will be deployed as a simple REST endpoint that takes in an object and stores it into DynamoDB. Nimbus uses annotations to configure the resources that will be deployed, with no large configuration files. It also provides clients to interact with the deployed resources in a simple and cloud-agnostic fashion. Nimbus supports many different resource and function types. At build time, Nimbus automatically generates all the required configuration, packages this together with the code, and deploys the minimal necessary change set to the cloud. This can speed up deployment significantly in large systems. When writing comparable applications, Nimbus has fewer lines of code, has fewer lines of configuration, has shorter deployment times, all without hurting performance. If this has interested you and you want to see Nimbus in action, come check out the full demo at the end of the session, where you can ask any questions you have. We hope to see you there.
Hi.
Thank you very much. So the next exciting paper is going to be presented by Giovanni Gurano, and the title is Testing with Fewer Resources, an Adaptive Approach to Performance-Aware Test Case Generation. Giovanni, go ahead.
Thank you very much for the introduction. So we all know that testing plays a very important role in ensuring software of high quality, but this is also a very expensive activity for developers. So to help ease this burden, like a lot of research try to automate the generation of tests, mainly exploiting evolutionary search and genetic algorithms in particular. So these approaches aim at maximizing code coverage criteria, usually branch coverage. But there are many other desirable qualities that we would like to maximize in our tests, like for instance, readability, code quality, execution time, or memory usage. So for this reason, a large body of research tried to maximize those qualities along with code coverage. But they all somehow fell short in doing so while keeping the code coverage high. In this paper, we focus on execution time and memory consumption as a secondary objective we want to maximize along with code coverage. And we proposed Hey Dynamosa, that Hey stands for adaptive. In this paper, we address 2 main challenges. The first one is about measuring the performances of tests that we want to optimize in the loop of the genetic algorithm without incurring in any performance loss for the algorithm itself. The second one, as I said, is to optimize both non-coverage and coverage criteria without harming the code coverage. So let us see how we address first the first of those challenges. So in our implementation, we need to measure the performance of tests to favor the test individuals that have better performance in our algorithm. To measure performances, we would like to do in an ideal world, like we would like to do a perfect measurement of performances, and this will involve running a test multiple times. But this is infeasible in the loop of a genetic algorithm because this would kill the performance of the genetic algorithm itself. So to address this issue, we devised 7 different performance proxies that are very easy and lightweight to compute, and that can approximate a more rigorous performance measurement. And we aggregate those metrics in a so-called performance score. So now let's see how we use this performance score to address the second challenge. So this is a sketch of the main loop of the genetic algorithm. It starts with initial population. This population is evolved into offsprings, and these offsprings are ranked into fronts. And usually, normally algorithms use the so-called crowing distance to rank individuals in each front. In our implementation, we use performance score along with crowing distance. So we start with performance score as a metric to optimize, to sort individuals in a front. And as soon as we detect stagnation in the fitness function, in other words, the algorithm is not able to improve anymore the code coverage, we switch back to crowing distance to optimize, to sort individuals in a front. And we keep evaluating at every generation if we want to switch back to performance score or to work with crowing distance. So when we work with crowing distance, we favor tests that are more diverse between each other, so we foster code coverage. When we use performance score, we favor tests with better resource demands. So we evaluated our approaches with a large set of Java classes, and we used Dynamosa, the state-of-the-art for multi-target approaches, as a baseline. And we asked ourselves 3 research questions. So we looked at the branch coverage between the 2 approaches, the mutation score, and we had a look at runtime and memory consumption. So for the first 2 research questions, basically for branch coverage, we achieve a very similar coverage amongst our subjects, and for a large part of the classes, there is no statistically significant differences in achieved branch coverage. And very similar situation we observe with the mutation score. So very quickly, we can have same achieved code coverage and same mutation score between the 2 approaches. Let us now see what happens with runtime and memory consumption. So to answer this question, we took subjects with no difference in achieved coverage, and we do this time rigorous profiling, the one that was not possible to do in the loop of the genetic algorithm. So we run those test suites for 1,000 times in a bare metal machine, in a fetch JVM, and we measure the runtime memory consumption. What we discovered at the end that on average, we are able to increase 70% lower runtime and memory consumption for those suites. So basically, main finding is that with the same coverage, we are able to have lower resource demands. So to wrap up, we proposed this approach called Adaptive Dynamosa that focus on test resource demands, so runtime and memory consumption as a secondary objective to optimize along with code coverage. But this approach is flexible enough and can be potentially used for any kind of possible secondary objective that is orthogonal to code coverage. This is part of a future agenda. So if you're interested, you can have a look at the preprint of the paper, and thank you for your attention, and I'm open for any question. Thank you very much.
Thank you very much, Giovanni. Great presentation. I start with a question from myself. You mentioned that you have multiple objectives here, basically the coverage and memory consumption and overhead in general. Did you have any preference over these objectives, and how diversity could affect these basically preference or the objective themselves? Thanks.
So the old point is we try to optimize a secondary objective. Actually, we started replacing completely the crowing distance, so not looking at all for the diversity in the population with the performance score. So we first looked at what happens if you completely replace crowing distance with performance score, and we don't look at all at diversity of tests. And we happen to see that we obviously can achieve good optimization in performances, but we lose too much coverage. So for this reason, we devised the system that can switch between the two and optimize both. So we still need diversity. We still need to ensure diversity in the population to keep the code coverage high.
Yeah, very good. Thanks. You have another question, but just quickly answer from Seamus. Does this coevolution assume that when switching from performance to the other function, there are no cross implication, i.e., one doesn't cancel the evolution of the other one? Just quickly answer that.
No, actually, there is no implication. Just the algorithm changes, which is the criteria to favor to do the sorting in the fronts to favor different kind of individual for the next generation. Basically, the population evolves is still the same, so there is no trade-off in that sense.
Awesome. Thank you. Let's move on to the next presentation. So this is another exciting journal first presentation by Diego Costa. What's wrong with my benchmark result studying bad practices in JMH benchmark? That's a very exciting presentation. Diego, please.
Thank you for a very nice introduction. Thank you all for joining me. I'm Diego. I'm going to be presenting an empirical study on bad practices and how that affects GMH benchmarks. So this study was done in collaboration with Krupal Bessemer from University of Alberta, Philippe Leitner from Chalmers, and Artur Andrzejak from Heidelberg University. So I don't think I need to spend a lot of time in saying how performance is important, but just to give you a glimpse on how critical it is for business efficiency, there's a report on Amazon showing that they would lose more than $1 billion a year just if the website slowed down by just 1 second. And because of the importance of performance, performance is dealt at many different levels during software development and management. And just to keep everyone on the same page, my talk is only about the code level, so micro benchmarks. So micro benchmarks are great if you want to measure things very precisely. For fine-grained performance assessment, you have a core method in an application that you want to have a very crisp performance profile, or you want to compare different libraries, different algorithms, or have a very fine-grained performance tests. And the tricky thing about benchmarks, however, is that they are really short running. So they run for milliseconds sometimes, and which makes it very easy to be affected by external sources like the operating system, the environment you're using, or in the case of Java, the JVM itself, which optimizes code at runtime and makes it quite tricky to write benchmarks in Java from scratch. So the community has come up with a few solutions, a few frameworks that would ease up how you would write your benchmarks. And the GMH, which stands for Java Micro Benchmarking Harness, is probably the most popular one. So GMH simplifies the creation of your benchmarks quite a bit. So let's say we have a method here, and you want a benchmark. All you need to do is write as you would write a unit test, annotate them with the GMH annotations, and GMH then generates all the boilerplate code, warm-ups, all this kind of thing that would make your benchmark, that will make you believe that your benchmark is really measuring what it's supposed to. The problem is, while it simplifies, it cannot guarantee that your benchmark is sound. What I mean by that is that if you look here, this benchmark is actually very simple. I'm just calling the method I want to measure, but I'm not actually using its return. So JVM would just look here and see that this code, this call, has no effect in my code. We just analyze it as a dead code. Would completely wipe away the code that I'm trying to measure. And that explains why I'm getting such fast readings, below 1 nanosecond, right? So to do that, you actually need to return the return of a method you want to measure. And this is one example of one bad practice that could affect your benchmark. So this is one bad practice that we studied. We studied actually in total 5 of them. I'm not going to dive into them because of time limits, but I definitely encourage you to read our paper because all of these bad practices, they are easy to identify, easy to find in your code, and most importantly, very easy to fix. And they all affect your benchmark in different ways. So the scope of our studies is that given these 5 bad practices, investigate how often do they occur and what is their impact in benchmark results. So So the first question we investigate, we need to find them in the code of the project. So we develop a static analyzer that would go in the code, bytecode parser, and will then spot bad practices for developers. So you can actually use this, our plugin. You can use in your IDEs, you can use in your CI pipelines. If you write GMH benchmarks, make sure your benchmarks are free of those bad practices. What we did then, we mined the GitHub repository. We found more than 100 projects that use GMH, and we run our static analyzer on them. And to our surprise, we found that 28% of the projects have at least one instance of them. But if you look at the projects that actually use GMH more extensively, so they have more than 10 benchmarks, this rises to like 51% of the projects. So it's very common mistake when writing benchmarks. And the example I gave you, not using return computation, is one of the most common, but there is another one that developers quite struggle with, which is using accumulation to consume values in the loop. You should definitely look at the paper to have more insights on how to avoid this particular problem. So the follow-up question is, okay, we know that they occur, but do they actually change the impact or distort the benchmark results I'm getting? And to do that, we selected a subset of projects, so 6 projects. You can all see them there. If you're familiar with the Java ecosystem, you will recognize a few of them because they're very popular. And we basically evaluate the benchmarks, the original version, and after we fix them, we run them several times, make sure that we're evaluating things properly. And what we found is that 78% of the benchmarks were impacted with large effect size. And of course, different bad practices impact them differently. So just to give you an example, this is an example of you run your benchmarks in the same VM fork, which you shouldn't do. You have to fork each benchmark in a separate VM. And you can see that the difference between the original benchmark and the fixed ones like 4 to 5 times. So the changes are quite substantial. So to validate our results, we submit pull requests to the benchmarks we fixed. Developers were all quite happy to receive them. Most of them actually knew about them, but maybe this was overlooked. We have one project that did rejected our pull request because they were thinking about removing GMH altogether anyway. And to summarize, we studied these bad practices, 5 of them that we select from the documentation. We found that they are prevalent, so they occur in quite a substantial share of the projects we investigate. They impact the benchmark results greatly, and we validate our results by actually contributing to those open source projects. So all the data is available. You can hit me on Twitter, and I'm now in Concordia University, and I'm glad to answer any questions. Thank you.
Awesome. Thanks, Diego, a lot for the great presentation. So Ian asking, what's the metrics that you used to measure the impact of fixing? If just time you change code, it's impact time, isn't that obvious? So please quickly answer that. We have only 1 minute.
Yeah, so we used execution time indeed, and we evaluate the distribution of this execution times between those different benchmarks. And we use the Cliffs delta to evaluate the effect size of these differences. And just to make sure, like we rerun these benchmarks in alternated fashion, we run them thousands and thousands of times. So the ones that we report, they really have very distinct, non-overlapping distributions. So to make sure that we are actually not introducing any variance while running our experiments.
Awesome. Thank you a lot, Diego. It was great. So the next presentation is so exciting. It's a distinguished paper towards the use of reality, readily available test from the release pipeline as performance test. Are we there yet? And the presentation is going to be done by Zisho Din. Thanks. Go ahead, Zisho.
Okay, I'm going to share my screen. Okay, thanks for the introduction. Thanks for attending the presentation. My name is Zisho Din from Concordia University. Today, I'm going to talk about our work on using readily available tests as performance tests. So we know that Performance is a very important aspect of software quality. So prior studies show that software system failures are often due to performance issues rather than functional bugs. So here is an example from Microsoft Surface Pro. We know that in this example, people always believe that short battery life was due to often due to hardware issues. But in the example, we found that the short battery life was due to a software performance bug. Before we go into our research, I want to give you a background on how to fix the performance issues. So generally speaking, developers will make changes to the source code, and then they will build and deploy the new system to the specially designed testing environment. While they are running the new system, they will monitor the performance. So after having the performance data, they will employ experts to analyze, to check whether there are performance issues or not. So, however, there is an obvious problem is that the performance testing is really expensive. So developers may need several hours or even days to collect the performance data. On one hand, testing is really expensive. On the other hand, testing is really important, and we cannot skip this step. So we wonder, do we have some kind of tests that are already executed and executed very often? So if so, maybe we can use the tests to measure the performance. So luckily, we found that we have functional tests that are readily available and are executed very often. Another good thing is that studies show that the tests are sophisticated. I mean, they're not so that trivial. So for example, in Hadoop, we found that there are more than 4,000 functional tests available. At the same time, we also found that these tests are executed on a daily basis. So we propose the first question, can we use these readily available tests to evaluate performance? So if so, it's a good start. So we perform an explanatory study. We choose two open source systems, Hadoop and Cassandra. The next, we are going to talk about a method to collect the performance data. So first, we will collect and label the performance issues from the issue tracking system. Next, we will identify the commits that fix these performance issues. After that, we will extract the impacted tests. When we have the impacted tests, we run all the tests and evaluate the performance. So next, we are going to talk about the details of each step. The first step is collect and label issues. So we will collect the performance issues from the issue tracking system. Here is an example from Jira issue tracking system. And generally speaking, we have 5 kinds of performance metrics. These are response time, CPU, memory, L write, and L read. And we will then manually label each performance issue with this performance metric. From this performance issue, we know that this performance issue is related to the response time. So we will do a manual labeling to the response time. Here, I want to mention that there are some issues are related to multiple performance metrics. So the next step is to identify the commits. We will identify the code commits that fix the collected performance issues. So for example, we have the performance issue and we will extract the issue ID. When we have the issue ID, when we search in the commit messages to get the commit that fixed the performance issue. So finally, we collect more than 100 commits that fix the performance issues. So when we have the performance issues, next we will extract the impacted tests. So first, we will calculate the test coverage. So we have a list of the impacted tests, and we will use some code coverage tools to get the code coverage for each Java file. And then we will get the commit changes for each Java file. If the test covered the commit changes, then we say this test is an impacted test. Next, we will evaluate the performance. We will run all the impacted tests and collect performance of each test. To avoid some noise, we run each test for 30 times. After having the performance data, we will perform a statistical analysis to get the p-value to see if there is a significant differences of the two performance. And then we will use cleavage delta to decide the effect sizes. So after having these performance data, now we are going to answer our research questions. Our first research question is, can these tests from the release pipeline demonstrate the performance improvements from performance issue fixes? In general, our results are really promising. We found that most of the performance improvements after an issue fix can be demonstrated by at least one test. For example, in Hadoop, we found that almost all the performance issues or almost all the performance improvements have been demonstrated by at least one test. However, we also found that only a very small portion of the tests can demonstrate performance improvements. So, what are the reasons that sometimes cannot demonstrate the performance improvements? So by knowing these reasons, developers may know how to improve the tests. To answer this question, we manually examine all the tests. We finally identify 8 reasons that a test cannot demonstrate performance improvements. So the most important one is too light workload. We know that functional tests don't have a so heavy workload to trigger the performance issues, and thus we cannot demonstrate the performance improvements. So here is an example of the too light workload. So from this issue report, we know that this performance issue can only be triggered when there are more than 1,000 keys. But in these functional tests, we don't have so many keys, so we cannot demonstrate performance improvements. The very last research question is, what are the important factors for a test to be successful as a performance test? To answer this question, we build random forest classifiers to understand the importance of metrics. All metrics come from 3 aspects. The first one is from test code itself. The second one is from code committed for issue fixes. The third one is from the code covered by test. And finally, we found that test code and code covered by test play an important role. So here we suggest practitioners should focus on designing and selecting the tests and may not need to optimize the test for different bug fixes. So we first propose our question, can we use the readily available test to evaluate performance? And then we propose a method to collect data. After that, we propose a research questions. And then we propose corresponding answer to these research questions. So thank you for attending this presentation. Any questions are welcome.
Awesome. Thank you, Zisho. It was great presentation, great work.
Thank you.
Please ask your questions. So I start with a question myself related to this. I was wondering, during your investigation, did you find out any performance issues related to configurations of
yes, exactly. Yeah, there are some performance issues are related to the configuration files. Yeah, they did a wrong configuration, so they cannot reach a very good performance. Actually, in our study, we don't consider this kind of performance issue into our study, as we only concentrate on the code itself. So we don't care about the configuration, the misconfigurations.
Yeah, that makes sense. That makes sense. But again, like configuration, basically the performance issues related to configuration also is relevant to code, right? Because these configuration after code
exactly
get executed, right?
Exactly.
So that makes sense that you did not basically look at these configuration issues in particular. Any other questions? We have 2 more minutes for questions. If you want to ask question, please go ahead.
So I believe there are a lot of there will be some works on the configuration issues, like.
Yeah, this is very exciting because I presume, especially for these 2 big data systems, that you look at configurations, highly configurable systems, right? And there are so many configuration-related performance bugs down there.
Exactly.
developers wants to discover. And this is in general a very difficult task, I would presume. Yeah, I'm still waiting for questions. We have 1 more minute to the next presentation. Still no question for this paper. Again, I highly recommend this paper. It's one of the most exciting paper I recently read. So if there is no question, apparently there is none. So let's thank you again, Zisho, for giving support. We move on to the next presentation. It's going to be done by Andreas Stan, and this is another Journal Fest paper titled Mode Guard, Identifying Integrity and Confidentiality Violation in Java Modules. Andreas, please.
Yeah, thanks for the introduction. My name is Andreas. So back in 2016, there was quite some rumor in the Java community concerning the release of Java 9. People were afraid if the new release may break the existing code. And the reason for this was the introduction of modules and the new module system Jigsaw. And at the first glance, a module looks similar to a traditional jar file. It groups a set of packages and resources. But in contrast to a traditional jar file, a module explicitly declares its dependencies. Here, for instance, my first module explicitly depends and requires a module named Java Base. And in contrast to a traditional jar file, a module explicitly states which packages it exports. Only my package, my public API. All other packages are kept module internal. And together with this module system, a feature called strong encapsulation was introduced. And for instance, if I have a second module that is allowed to read my first module, then all classes in the second module may only access exported classes and types. Any access to internal packages of the first module is prevented by the virtual machine.
Excuse me, it seems there is a problem with the screen. Could you please stop sharing and start sharing again?
Okay.
See the full screen.
Sorry.
No worries.
Does it now work?
No, same problem again.
Same problem again. Oh, it worked in the test run.
Don't worry at all. Take your time.
No?
No. I'm so sorry. Maybe someone from the virtualization team can help here.
Strange. The different screen?
Still, no, it's maybe if you could fit this into this small window, maybe, yeah, that would be still better than nothing, right?
Oh, sorry.
Yeah, I would leave it to Sergio to advise.
Better?
Yeah, if you move it to the left, then yes, yeah, and then make it larger, right?
Oh, sorry.
Yeah, a little bit smaller, a little bit more. I'm so sorry. Yeah, this is better. At least we can see the whole thing.
Oh, strange.
Yeah, go ahead.
Okay, the driver worked. But okay, so the module system now explicitly declares what packages are external and which packages are internal. And the strong encapsulation ensures that the guarantees are met. And even if I use reflection in my second module, any access to the internal types is still prohibited. Given this clear module boundaries, we ask ourselves, can we use the module system and modules to confine internal data within modules? And can we design a static analysis to track unintended data flows that violate confidentiality, so that internal data flows outside of the module or that violates integrity, that internal values of module internal fields, for instance, can be changed from the outside. And finally, we ask ourselves, can one use the module system and can real-world projects benefit from it by migrating to modules? And to get an answer to the first questions, we formally defined what constitutes an entry point of a module using the data log engine dupe, and we identified two entry points constituting a module. First, explicit entry points that are the public and exported classes in exported packages, and implicit entry points. These are the not so obvious ones. These are methods of internal classes that become reachable as a result of the invocation of another entry point. So when an exported method hands out an instance of an internal class to the outside that exports, overrides, or implements an exported interface. And given this module definition, we defined an escape analysis specifically for modules to discover integrity and confidentiality violations. To give an answer to the third question, if real-world benefits can benefit from the module system, we migrated Apache Tomcat to Java modules, and therefore we took the jar files and did two modularizations. First, a naive approach, where we used JDEPs and migrated each jar to a separate module, and a strict modularization, in which we removed all non-necessary exports from the resulting modules. And to check our analysis, we run modguard on each module to detect violations. To detect internal fields, methods, and classes inside the Apache Tomcat modules, we use the machine learning approach SUSY. And our results show that the number of violations does not heavily differ between the naive and the strict version. So to complete, what does it mean for the module system? So the module system can confine types from escaping, but it does not prevent data and internal instances from escaping. But module analysis and escape analysis like modguard can complement the guarantees the module system provides by discovering unintended data flows through which internal data types, classes, and methods and values may escape. Real-world projects may only partially benefit from the module system, as the number of violations shows in both versions that not a simple migration just to modules is not sufficient, but the architecture of the projects needs to be reworked. Okay. Oh, so, thanks for your attention, and sorry again for the technical hassle, because yeah, in the dry one, there was no problem.
Thanks, Andreas. It was great presentation. Yeah, this kind of interaction box happens all the time. No worries at all. It was great. People enjoy it. Unfortunately, we don't have much time for any question here. But let's move on to the next presentation. So it is an exciting presentation, a near presentation actually, program the bloating via stochastic optimization, and is going to be presented by Ki-Jin. Ki, please go ahead. Thanks.
Thank you for the introduction. Can you see my slides okay?
Yes, perfect. Go ahead.
Okay. Hi, my name is Ki-Jin. Today I'm going to talk about our work, program debloating via stochastic optimization. Today's programs are complex and contain abundance of unneeded features which can severely harm the performance and security of a program. So program debloating techniques aim to eliminate the unneeded features of a program and create a reduced version. Existing debloating techniques tend to take size reduction as the only goal. Although effective, they only look at one side of the problem, and they don't consider cases in which programs' additional behaviors may be exercised. In fact, there's a tension between reducing the size and being able to handle inputs that may not have been observed before. That means the more code you reduce, the less general the program would be, and vice versa. So debloating is actually a multifaceted problem, and it should allow for multiple, possibly conflicting goals into play. Motivated by this, we formulate debloating as an optimization problem, and to solve the problem, we propose a general approach that lets the user provide a program that is bloated, a usage profile as a set of inputs, a set of factors that are of interest, and weights for these factors. And we define an objective function that computes a score to quantify the trade-off between these factors. The goal then is to search among a pool of reduced programs to find the one that has the highest score. So this is our general approach. We also present debop, a specific instance of the approach. For debloating, debop takes into account 3 factors: size reduction, attack surface reduction, and generality. It uses an objective function that is defined based on these 3 factors, along with 2 weights. And it performs an MCMC-based stochastic search to explore the search space. We did a case study by applying a prototype of debop that we implemented to a Unix utility, make the error. We compared debop with Shizo, a state-of-the-art reduction-oriented technique. And our results show that debop is able to produce debloated programs with different trade-offs using different ways. Although Shizo achieves higher size reduction, debop, by taking into account the attack surface as a debloating factor, achieves higher attack surface reduction. To conclude my talk, I discussed debloating as a multifaceted problem. And to solve the problem, we propose a general approach that performs optimization to achieve debloating. I presented a specific instance of the approach debop and a proof of concept evaluation. As future work, in addition to performing an extensive evaluation, we would investigate other ways for program mutation and stochastic search for better optimization. We would also apply our approach to other areas, for example, to reduce energy and improve efficiency. And if you want to know more, please read our paper and check our debop tool. Thank you. I'm happy to take questions.
Awesome. Great presentation, Keith. It was great work. Please ask your question, audience. I have myself a question. What was the main insight with respect to this difficult problem with respect to exploration? Because exploration matters a lot for this multi-objective optimization, and maybe a preference over the objectives that you have could help. Do you have any insight or thoughts here?
Yeah, actually, the search space is very large, and so yeah, you need to. Well, as I mentioned also in the future work, there are the 2 factors that we need to consider improve. One is that what is the model of your program, and currently we use a model representing the program as a bit vector, and each bit actually representing a statement, and flip the bit to generate new programs and generate samples, and we would investigate other models, maybe more sophisticated models, to better explore the search space. And another way is what is the stochastic type of stochastic search you use. And currently we are using MCMC based search, and but we could maybe try other types of searching technique to improve, and we'll look at this in the future work.
Yeah, great, great insight. Yeah, basically augmentation of additional knowledge would help exploration around. Thanks, very good. We move on to the last presentation in this session, and this is also another very exciting work. Is going to be presented by Marco. So the title of the paper is the ORIS tool, quantitative evaluation of non-Markovian system. Again, this is another journal first paper. Marco, please go ahead.
Yep, sharing my slides. Okay, can you see my slides?
Yes, go ahead.
Great. So welcome everyone. My name is... In fact, ORIS is actually the result of a line of research spanning over 20 years, devising methods to analyze stochastic processes produced by these models under different constraints on the distribution of transitions. General non-exponential timers are important to fit experimental data, but they result in non-Markovian processes, such as semi-Markov processes or Markov regenerative processes. Nonetheless, ORIS is able to analyze these numerically and not only by simulation. The second use of ORIS is as a library. Very often the user is not interested in the analysis of a single scenario, but in the evaluation of many system designs. To automate the construction and analysis of stochastic models, ORIS includes a Java library called Serial. This library can be used to create extensions of the model formalisms or new analysis methods, or to implement software components that use models at runtime to adapt to the environment in which they operate. Finally, ORIS can be used as a toolkit to develop applications that construct and analyze models with its Java library. How does that work? Well, the user can define, analyze, and validate models using the application, and then export them as Java code. This code can then be imported in a Java IDE like Eclipse and used to build models using the library. Over the years, this approach has been used by several research works in the areas of railway signaling systems, real-time software, repair procedures for gas and water distribution networks, and online activity recognition for ambient assisted living. Overall, the use of ORIS as a graphical application, library, and toolkit greatly simplifies the development of services based on stochastic models. The example here is about a predictive analytics service for a bus stop, where passengers arrive as a Poisson process, but due to social distancing, only up to 10 are allowed to get on the bus, which arrives at regular intervals with random delays. The development of these services usually follows a process which starts in the ORIS application with the design of a stochastic model together with metrics such as rejection rates or wait times for the passengers, and then an object-oriented domain model is developed, can be defined in Java to collect information for the different instances of the problem, such as bus lines, timetable, passenger arrival rates, and so on. Now the Java code exported from the initial ORIS model can be used to build a model builder which visits this domain model to construct different instances of the ORIS model, and the analysis can be part of facade objects that start the analysis to evaluate metrics at runtime or offline. In our experience, ORIS can also serve as a tool to teach stochastic models and the design process of services that use them, and is freely available under an open source license. We have tutorials on the website, and I'm glad to take any question about ORIS.
Awesome, awesome. Thanks, Marco, for great work and presentation. So please ask your question. We have 1 more minute. I start with one question myself. So I presume this stochastic battery net that you mentioned, and thanks for making it relevant to the COVID situation now in your example. I presume basically these are specified by a human, right, person. How confident you are that this kind of a specification could not impact the analytics in a biased or incorrect way?
That is up to the modeler, of course. So as in any model-based evaluation, the modeler has to develop a model and then validate the model with respect to the real world.
Mm-hmm. Awesome, awesome. So there is no guarantee in your tool, basically, to check that automatically.
That the model is correct? Yeah. No, but normally the user would develop the model, obtain some metrics, and then compare those metrics with measurements from the real world, from real systems, and check that the model is accurate. Then the model can be used to predict in other scenarios, to see, to respond to what if questions. For example, if we speed up the processing rate of a server, or if we increase the frequency of bus arrivals, what is the expected rejection rate or wait time for the passengers.
Awesome, awesome. Thank you, Marco, for the great work. So unfortunately, we have to conclude this exciting and great session. So I have something to say. Please look for the presenters of this session in the lobbies video chats during the third hour. You can also visit SRC posters, the demos, attend the Ask Me Questions session by Bashar later on, and stop by the Facebook booth. Thank you for attendance, and looking forward to talk with you soon. Thanks, it was great.
Thank you, everyone.